In this video, we will be covering parametric and polar arc length. So first we'll start with finding parametric arc length. Let's say that our curve L is parametrized by x, some function of t, and y, some function of t. We can approximate the length of the curve with line segments, which we have briefly explored in our first arc length video back when we were dealing with just the arc length of y equals f of x. So go back to that video to see the geometric argument for what's happening, and then generalize that to the fact that when we have these curves parametrized and we're looking to find the length between t1 and t2 for this curve, we get it from the formula. The arc length is equal to the integral from t1 to t2 of the square root of dx dt squared plus dy dt squared. So using this formula, we'll just do a couple small examples of arc length because it's pretty straightforward once you've got the handle of plugging into the formula. Our dx dt, for this first example, we're trying to find the arc length of the curve defined by x equals 3t squared, y equals 2t cubed from 1 to 3. So computing our dx dt, we get 6t, and our dy dt, the derivative would be 6t squared. And plugging into our formula, we are going from 1 to 3. We are computing the square root of 6t squared, so 36t squared plus 36t to the fourth dt. And that gives us we're computing that integral, and when we compute the square root here, thinking about what is going to be helpful, if we broke this integrand up into square root of 36t squared times the square root of 1 plus t squared, I think that would help tremendously. We'd get 6, which we could factor out, a t which we cannot factor out, still integrating from 1 to 3, and we have 1 plus t squared dt. Okay, the reason I think that that is particularly helpful is because I can now see that I have a u sub opportunity. So if I let my u be 1 plus t squared, my du would be 2t dt. And if I add in a correction factor of 2 and a half to the outside of the integral, I now have my u sub ready to go. So if I do my u sub, remember I also have to change my limits. So my limits for integration are going to become 1 plus 1 squared is 2, and 1 plus 3 squared is going to be 10. So I have 3 integrating from 2 to 10, u to the 1/2 du. So I get 3, and then 3 over, see, adding 1/2, upping 1/2 would give me 3 over 2, so 2 over 3. Okay, so I get 10 to the 3/2 minus 2 to the 3/2, and that's multiplied by 2 for my answer. Okay, so basically I would say that the difficulty in finding arc length simply lies with the normal difficulty in terms of integrating and where your integration skills are at. Okay, let's take a look at finding polar arc length. So this formula is going to come directly from applying the parametric arc length formula to the fact that x is equal to r times cosine theta and y is equal to r times sine theta. And when you use those formulas for your x and y, your polar arc length formula becomes the arc length is given by the integral from starting angle alpha to ending angle beta, square root of r squared plus dr d theta squared. Okay. So the arc length of the cardioid, 2 plus 2 cosine theta is our first example. We will compute what is f of theta squared. Would be 4 plus 4 cosine theta plus 4 cosine squared theta. And then what is f prime of theta? It would be 2, okay, so it would be negative 2 sine theta. So then f prime of theta squared is going to be 4 sine squared theta. So when I go ahead and compute this integral, it doesn't say what is my starting angle and what is my ending because it wants the entire arc length. So because I know that the curve is going to start repeating once I hit 2 pi, I'm just going to go from 0 to 2 pi and then to get one sweep of the curve. And you can confirm that with graphing technology. So I'm computing the square root of 4 plus 4 cosine theta plus 4 cosine squared theta plus 4 sine squared theta d theta. And I'm going to clean this up a little bit. I see a cosine squared plus a sine squared with 4 out front. That's awesome because that's my Pythagorean identity. That's just 4 times 1. Okay, factor out the 4 and you're left with the Pythagorean identity. So we get 0 to 2 pi. 4 plus 4 is 8 plus 4 cosine theta d theta. And this is going to be a very interesting yikes. Sorry, I expanded out my f of theta squared incorrectly. So to catch the change, when we do 2 plus 2 cosine theta, when we square that, we'd have 4 cosine theta plus 4 cosine theta. So this should be 8. And this should be 8. And this should be 8. Okay, so to integrate that, we're going to use the fact that we actually have I don't want to do a trig substitution here because I already have a trig function inside the integral. So this is definitely a very tricky integral, which is why we're kind of looking at it together here. I'm not going to do a trig sub when there's already trig functions present. I don't see a u sub that's coming up. So the best bet is going to be to use the fact that cosine 2 theta is usually equal to 1 plus, cosine squared of theta is equal to 1 plus cosine 2 theta over 2. So then solving this for cosine of 2 theta, we get that 2 cosine squared theta is 2 cosine squared theta minus 1 is equal to cosine of 2 theta. And then if I add 1 to both sides and multiply by 2, I get I get 2 cosine of 2 theta plus 2 is equal to 4 cosine squared theta. So we're getting somewhere nice. If I factor out a 4 from this, I'm left with 2 plus 2 cosine theta. Okay, I can break my square root up and bring that 2 out. And then I'm left with square root of 2 plus 2 cosine theta. And I'm looking at this trig identity and thinking, ooh, this is almost what I want. I have 2 cosine 2 theta plus 2, and that is very similar. The only thing that's different is I need to transform this trig identity to have just a theta inside. So if I go ahead and let alpha equals 2 theta here, then this side equals alpha over 2. So now I have a trig identity that looks exactly like what's happening over here. So if I go ahead and use this trig identity, we're going to use the left-hand side to rewrite this integral to 0 to 2 pi. And this is now becoming the square root of 4 times cosine squared of theta over 2 d theta, and that'll simplify to 2 cosine of theta over 2 d theta. And we square rooted a square root, so we need an absolute value. And since cosine switches between negative and positive, if we went ahead and split this integral up and we did 2 times the integral from 0 to pi, cosine would always be positive. So I can go ahead and drop those absolute value bars. And then this integral ends up being 8 times sine of theta over 2 evaluated from pi to 0, which gives us 16. Okay, quite a lot of work on the integration here. This is definitely a very challenging integral. Is it something that I would, whenever I show challenging things, there's like a love-hate relationship because people are like, okay, yeah, now I feel prepared to do this on like the homework, but oh my gosh, I never would have thought to do this myself. Yes, this one is very tricky. I would take a while to figure out how to do this one myself as well. However, that's why I'm showing it to you, just to show you how we can sometimes use these trig identities to our advantage. I would not expect someone to just come up with this for the first time on an exam. I definitely would not expect that. So please temper your fear a little bit and just embrace the challenge that is working with these interesting integrals. So this is our final example for arc length, and I think it was a very meaty one. In our next chunk of videos, we're going to be delving into the world of sequences and series and completing the typical Calc 2 class at that point. So I will see you then.